We are now going to go back and revisit objects rearranging themselves and platforms shifting. But now we're going to do it from the perspective of conservation of momentum. So, why conservation of momentum? Well, if there are no external forces, so sum of the external forces, right, equals 0. So everything is internal. The people are just walking on platforms again. So we have our person here is just going to walk on the platform. This person is going to move to the left, and we'll talk about that in a moment. The platform is going to recoil and shift to the right. And from our conservation of momentum perspective, if sum of the forces external equals 0, then remember that delta P over delta T also equals 0. So that means delta P must equal 0. So P initial equals P final. And what that means is that if there was no initial momentum, so in this case we are talking about starting from rest, there's no initial momentum. So that means there has to be no final momentum, and that the momentum of the man to the left must at all times equal the momentum of the cart or the platform to the right. So let's see what's going on here. Let's erase this. All right. So what we're going to do is calculate the motion of both of the particles as they're in motion. So P initial equals P final, because we now know there are no external forces, momentum is conserved. There was no initial momentum, so the momentum of both the man and the cart was 0, so we have 0. Now, in other problems, you could be given an initial momentum. You just plug in whatever you're given for the problem, but in this case, it's 0. Now, the motion of the man, we are told, is 1 meter per second relative to the track, and that is important relative to the track because the conservation of momentum equality, so this red P initial equals P final, is always only valid relative to the ground. So we have to be looking at it from the perspective of someone standing on the ground. So please make sure that your velocity values are always with respect to the person on the ground, and we're going to reinforce that and emphasize that as we go along as well. So we know that the velocity of this 70 kilogram man to the left, that's why the negative is there, and it's 1 meter per second, is the momentum of the man. So the momentum of the cart with respect to the ground is going to be our 1,000 kilogram cart times the velocity of the cart. We can then calculate the velocity of the cart, the recoiling, that movement of the cart to the right as the man moves to the left is going to be the 0.07 to the right. This is where the problem gets to be a little bit tricky if they go on and ask you to solve for how long does it take the man to go from where he started at the end of the cart to be able to touch the flag at the front of the cart. The reason it's a little bit tricky is because we just calculated the cart is recoiling to the right at 0.07 meters per second, which means that flag is actually moving towards him at 0.07, so that the relative motion between the man and the flag, or the front of the cart, is going to be 1 plus the 0.07. So, I know, that's a little bit tricky. So it's going to take a little bit less time to move the 10-meter distance of the cart, if it's a 10-meter cart that we have here, based on the fact that the cart is in motion. Now, when the man stops walking, in this case, it doesn't matter that the cart is enormously heavy. So you don't get fooled into thinking that the inertia of the cart is going to keep the system moving. It will not. The initial momentum of this system was 0. So the final momentum must be 0. And when the man stops walking, the cart must stop moving as well. So again, this chapter 9 has a lot going on in it, and I know there's a lot of new concepts. So please make sure you annotate your notes very carefully, and we will talk about and discuss these concepts in class, and you need to be proactive and ask your questions.